hello there. Welcome, come on in. This is EDP 308 Statistical Literacy, and I am Miss Raz, here to guide you through your journey of becoming statistically literate. So, without further ado, let's get into it. At the beginning of all of my lessons, I will have a brief overview for you to let you know where we will be heading on that particular lesson. Today, we're going to cover some course goals, talk about statistics in general, have some examples to think about, address extraordinary claims, talk about communication and how science and society interact, we'll introduce the idea of data, and I will introduce you to the Statistical Software R. Oh, my heart. First up, some of the course goals. This is not an exhaustive list, but ideally, by the end of this, you will have an understanding of the two main types of statistics, which are descriptive and inferential. You'll be able to evaluate the quality of research articles, news stories, headlines, or some other statistical finding by being able to ask good, poignant questions like, how was the study conducted? How many participants were there? How much of an effect did this really have in the real world? And you will gain experience calculating statistics and running some code in the wonderful statistical software R. Statistics! What's the point? Stats! What is it good for? Absolutely everything, with the caveat that it has its limitations. So what's the point of statistics? What are statistics used for? What good is it to provide an average of something like the average test score or the average amount of lead in US water? Why do we care about the probability of something happening or not? Why? Why does it matter to me? So here are some of the uses of statistics. So knowing the average, let's say, test score can give me an idea of how my class is doing, how learning is going. Or you can also think of it another way, and I could ask myself, how well am I doing teaching the material? That test grade might be a reflection of me too. And how about the average amount of lead in water? Why do we care about that? Well, if we know what the average is, we can know what well above average is, and then we can investigate when we see a water sample that has a lot of lead in it. And probability can help us determine things like how likely or unlikely is it that we see a city that has lead levels that are 5 times the national average. What's the probability of that? One of the other main goals and main points of statistics, we have descriptive and inferential statistics. Descriptive statistics do just that. They describe things. They usually summarize down to just one number, but sometimes we lose a little bit of information when we summarize things like that. Still incredibly useful and helpful. Inferential statistics gets a sample of data from a population, because we usually can't sample everybody in a population. So we take a small sample, do some mathematical magic, and then we can make inferences to the population at large. We can also assess the probability of events, because that can help us reduce or prepare for risky situations. For example, what's the probability that you're going to break your new iPhone in the next 2 years? Should you purchase that extended warranty? Depends on the probability. And we can also identify important relationships where it might be unethical to test it empirically. So, does smoking cigarettes cause cancer while controlling for confounding variables? Now, most of us, of course, know that yes, cigarettes are bad for you and can cause cancer. But there are a lot of other things associated with smoking. People who smoke are also more likely to engage in other risky behaviors, not exercise very much, or have poor diets. So we have to parse all that out. And we can do that by identifying some important relationships using statistics. But what about...
We have lies, damned lies, and statistics.
En contraire, Mr. Twain. Statistics are not lies, nor do they lie. They're statistics. Only the people who use statistics inappropriately or for their own agendas lie. But statistics do indeed have their limitations. So data and the statistics we decide to run on that data can help us understand, but statistics do not tell you the correct answer, do not live in isolation. There is always some sort of context to take into account. They do not select and run themselves. There are a lot of statistical tests out there, and you have to pick what's appropriate based on your data. They don't flush out every other possible explanation. You might have failed to measure some important variables. They can be misinterpreted to push an agenda, and we will see plenty of historical examples of that coming up. They are not interpreted the same way by everybody. One person could read one statistic one way, another person could read it the exact opposite way. And statistics are only as good as the data that you put in. There is an old phrase called garbage in, garbage out. Just another moment on that garbage in, garbage out. We have Charles Babbage, who was a very famous mathematician. And he was quoted once as saying, "On 2 occasions I have been asked, Pray, Mr. Babbage, if you put into your machine wrong figures, will the right answers come out? I am not able to rightly apprehend the kind of confusion of ideas that could provoke such a question. In other words, Charles here was saying, you think that if you give me bad data and I put it into my fancy little machine, you're going to get the right answer? How can you even ask that? So, yeah, garbage in, garbage out. Think about it. So let's go through a few examples and think about them. Let's say that there are two students sitting next to each other. They take a 50-question multiple choice test, and they both get 5 of the questions wrong, 5 out of those 50. Do you think that they were cheating? Maybe, but I mean, it's not crazy to get 5 wrong out of a 50 multiple choice test. You might be asking, well, which ones did they get wrong? So let's move on to scenario number 2. These two students got the same 5 questions wrong. Were they cheating? Well, I mean, maybe they were really hard questions, right? Maybe those were the 5 hardest questions on the exam, and a lot of people miss those. Okay, now the next question you might be asking is, did they have the same answers on those 5 questions? So that's scenario number 3. These two students chose the same wrong options for the same 5 questions. Were they cheating? Again, it seems like the odds of them cheating are going up because though it's possible, right? I mean, maybe those 5 questions were really hard and there was one wrong answer that looked really good, that maybe looked like the right answer. So maybe they weren't cheating. Now, in all these examples, I don't have an answer for you right now. This is just to start getting you to think about these things. Now, what's really important, and we will see this as we continue when we start testing things in statistics, what are the chances of each one of these happening, assuming that they were not cheating? If we're going to assume that these are honest students, what's the probability that 2 students get 5 wrong, 2 students get the same 5 wrong, and 2 students get the same 5 wrong and the same 5 wrong answers? These are very important distinctions, and this probability is going to be so awesome when we get there, but that's later. How about an extraordinary claim? Amazing new natural deodorant has over 9,000 5-star reviews. I actually heard this once on a podcast advertisement. Is this the best deodorant ever? What would be a more accurate thing to report? Maybe like what percent of all those ratings were 5-star? Because maybe they have 9,000 5-star reviews, but maybe they have 18,000 1-star reviews. They're being selective here. So why would someone want to misrepresent some data? Plenty of reasons. In this case, they probably want to sell their new amazing natural deodorant. Does everyone love it? Do you know? We don't, because they are very much hand-selecting what they want to present to us. Here's another one. A new study finds that exposure to the household cleaning product chemical sounding cleaner increases your risk of a very specific type of cancer by 100-fold. Should you never use that cleaner again? Well, I mean, does it work? Is it good at cleaning stuff? No. What you need to know, what's the important fact here? This very specific type of cancer, what were the chances of me getting it to begin with? If they were 0.000000001, and now we've increased that chance 100-fold, well, it's still going to be 0.00000 with a few less zeros back there. So this is a little bit misleading. And let's take some advice from the late, great Carl Sagan. Ah, you're so awesome. Extraordinary claims require extraordinary evidence. I miss you, man. Moving on. Extraordinary claims. So let's talk about some of these extraordinary claims. Surely you've read some sort of crazy fact like, new study shows drinking this soda causes this certain type of cancer. Many times the media will publish what sounds like an extraordinary claim as a fact. But in reality, many times the researchers in the study itself make no direct claims that something is the direct cause of something else. Causation is actually very difficult to establish and requires really rigorous experimentation. Why then would media or even well-respected research journals publish such a claim? Perhaps they have their own agenda, clickbait, views, monetary gain, professional success? Who knows? But these are the kind of questions you need to keep in mind when you read an extraordinary claim. So here are some of the questions that you can ask when you read a news article or a research article, or if somebody just makes some sort of assertion like, I heard once, or they said, you can ask, well, who funded it? Who funded that study and that research? Did they have their own interest in it? Do they want to find a certain type of finding? Like Pfizer, if Pfizer is making a drug, well, they probably want to show that that drug works. And if it doesn't work, they might decide to suppress that research. You can ask, how big was the sample size? Was it just 10 people, 100 people, 1,000 people? Sample size is very important. What was the research design? Was it appropriate? Are they trying to establish causation from some sort of correlational study? That would be completely inappropriate because surely you've heard that correlation does not equal causation. What kind of statistical analysis did they run on it? And what were those statistics? Were they significant? What was the effect size? And is the data freely available? This is a new push in science to start publicly posting your data for other people to try to run the statistics that you did to see if they get the same results. Now let's talk for a moment about some poor research. Andrew Wakefield. Have you ever heard of him? This is an example of how one poorly conducted study can ripple out and affect society in very deleterious ways. So maybe this will give you a clue as to what I'm about to show you. Wakefield et al. 1998. Ileolymphoid hyperplasia, nonspecific colitis, and pervasive developmental disorders in children. That's a mouthful. What are you looking at? Yep. This is the paper that started, or at least definitely fueled, the MMR vaccine autism controversy, the idea that vaccines cause autism. They don't. I don't need to tell you that. In 1998, Andrew Wakefield, along with 12 authors, published this article in The Lancet, which is one of the most prestigious research journals out there. In 2010, a full 12 years later, it was finally retracted, meaning they pulled it back and said, whoops, we shouldn't have published that. That actually was bad research. So let's actually read some of what the paper said. Quote, onset of behavioral symptoms was associated by the parents with measles, mumps, and rubella vaccination in 8 of the 12 children. We had a sample size of 12. We identified associated gastrointestinal disease and developmental regression in a group of previously normal children, which was generally associated in time with possible environmental triggers. So what is this kind of saying? Well, we're saying that it's the parents who thought that after the MMR vaccine was administered, that's when they said, my child started to change, there was behavioral changes, and that is what caused the autism possibly. Okay. Now let's discuss Andrew Wakefield himself. Okay, so he was an MD. He lost his license in the UK for all of this stuff. So here are just some of the issues. He had a financial conflict of interest because he had a different vaccine patent for a safer vaccine, and he was somewhat in cahoots with some of the lawyers trying to sue for vaccine-related injuries and damages. There was some professional and research misconduct. He used his own patients and he forewent IRB protocols. The IRB is basically a research and ethics committee that you have to go through them and explain exactly what you intend to do to any participants to make sure that everything is ethical. Yeah, he just went, nah, it's fine. They're my patients. I'm going to give them whatever test I want, even potentially unnecessary ones like lumbar punctures and colon biopsies. That's a no-no. That's a big no-no. And it was poor science to begin with in that there was only 12 subjects. There were actually more authors on the paper. Of some of those 12 subjects, some did not even meet the actual requirements for certain diagnoses. And, of course, correlation does not equal causation. No. 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 Now that we've seen one bad example, let's move on. Communication, science, and society. One of the understated but crucially important parts of statistics is effective communication of those statistics. You could be the most brilliant biostatistician out there discovering cures for things left and right, but if you cannot communicate your findings to your peers or to the public, your work could have no real impact and you could be completely forgotten. But communications and statistics needn't fall only on those people doing the statistics. For example, journalism departments have started to realize the importance of understanding and communicating the numbers as well as creating engaging visualizations to help get the message across. Even here at UT, the communications department has started to add more visualization and statistics related courses to help these journalists get these messages across. So ideally, we would have journalists, science journalists who are communicating these findings with high fidelity and not exaggerating anything. But, I mean, try to read a research article. They're not very interesting. We usually want some sort of journalist to make it more interesting, add some flair, but not at the expense of what the actual message was. So maybe you've seen something like new cure for autism discovered. I mean, that is a no, that it's not. It might be a new possible treatment or something, but a cure? Come on now. Or perhaps something more recent to us. Masks do not help mitigate the spread of COVID-19, and then shortly after, masks do help mitigate the spread of COVID-19. So what are some of the pros and cons of pop science headlines? Take a moment, think about it. Have a second with yourself. Think about some of the headlines you've seen before. So one of the best pros of pop science kind of news articles is that people are engaging with science, and that's fabulous. We need more of that in our society. Desperately. But one of the cons, unfortunately, can be that if an irresponsible journalist or writer maybe inflates a claim a little bit, people are going to run with that and maybe use it to push some sort of agenda that they have, and that's a no-no. That's not okay. Now, this example is not too egregious, but let's just look at this and see the difference between what a headline said and what the actual paper said. So here, from Science News, which is a fairly respected, little science publication, it says COVID-19 causes hyperactivity, in quotes, in blood clotting cells. Okay, but I was able to go and find the real paper, and the name of it, Platelet Gene Expression and Functions in COVID-19 Patients. Okay, so look at that title versus that title, very different. And secondly, this is really their main finding. These findings demonstrate that the COVID-2 infection is associated with platelet hyperactivity, which may contribute to COVID-19 pathophysiology. Now, look at these words here. Associated, may contribute. These are suggestions that it might be doing something. This is directly stating that it causes this. Not okay. Got to be careful with wording like that. So what's really important to note here is that COVID may indeed be associated with platelet hyperactivity and may indeed cause some of these changes, but more data is needed. Sometimes there is some evidence for a finding, but many times it is limited, especially right now in the early stages of research. More studies with more participants usually need to be conducted. This does not completely discredit any sort of findings though, but we just need to remember to take them with a grain of salt and always be willing to update our current understanding when new information and data become available. Some people do not like this about science. They'll say things like, oh, well, 10 years ago it was this, and in another 10 years it's going to be something else. Yes, science is self-correcting. The more research that's done, the more we realize that one of our previously held theories or beliefs might have been wrong or needs to be improved, and that's great, and it needs to keep evolving like that. Like with the COVID-19 mask thing, at first it seemed that it wasn't that helpful, but more studies were done, and now that we realize the scale of the pandemic, every little bit helps. So wearing a mask does help, and you should wear your mask out if we're still wearing masks at this point, which we might be. But this is the essence of being a good researcher and a statistically literate member of society, looking at the numbers and updating your own beliefs as new data comes in. Open it up! So in the last few slides, I showed you an example of a headline, and I showed you an example of the actual research article that headline was citing. Now, unfortunately, most of the general public cannot go and access the original article. I was able to because I am currently here at UT as student and employee, and so I have access to all the research and the literature because UT pays a very hefty fee for it. I guess we do too, as our students paying tuition, but anyway, most people do not have access to that. If you wanted to read that one article and it's not open access, you would have to pay $30, $40, $50 for one research article that might not even be relevant to what you were trying to figure out. So this video here is the first in your watch and react assignments. It's called Open Access Explained, and it's going to explain what this closed and open access means. Give it a go. Tell me what you think about it. I am very passionate about this. Open access. Data! What do we mean when we say data? We looked at the data and found XYZ. The data showed ABC. The data were collected through a randomized controlled design. Data is merely the raw materials of knowledge. Something from the New York Times. What is data, though? Data is plural, and it's very easy to mix the two. Data is, data are, it's data are. So data are the measurements that you've taken, the responses that you've gathered, the value of something that you measured, the value of a variable. And let's have an etymology moment. The Latin word data is the plural form of datum, thing that is given. And it basically means like dar, to give. If you know Spanish, like Dar something means to give. So it's like a given point, a given data point. So it's a given fact that I'm about 5'6". That is my data point, and it's a given. I love things like that. That's just me. Up next, before we dive into statistics, we first need to understand the different types of variables, how those variables are measured, and how variables can be used in research. So up next, we're going to talk about variables. I will see you there. But not before we discuss the Statistical Software R. Now, at the end of some of my lessons where I have examples, I will show you how to do some of the things we do by hand in R. So let's talk about this hand calculations versus software. People who do statistics like as their job never calculate anything by hand unless they are maybe working on developing new statistical techniques. In that case, they would maybe be making equations. But it is very useful still to do a few examples by hand to see how the calculations work and where certain values come from. In this class, you'll have some assignments where you have to do some calculations, and you have the option to either do them by hand, because I will show you how to do those, or to do them in R. I will provide you examples on how to do those too. I strongly encourage you, though, to use R whenever possible, because practice with R helps. And you'll eventually have this group project at the end, so all the practice you can get is probably a good thing. So what is R? For this class, you will download the free software R. R is basically a giant fancy calculator. It's amazing. And it's completely free and open source statistical software. Another great one out there is Python, but we won't cover that. There are many other types of statistical software out there like SPSS, SAS, M+, MATLAB, and others. However, these are all proprietary, meaning that they cost money to purchase and use. Excel can do some things too, but technically Excel is also proprietary. You have access to some of these as a student at UT using the remote access thing, but let's just learn R. It's free. You don't have to worry about graduating and not have access to it. One aspect that some people find intimidating about R when you start is that you do have to do a little bit of coding. But it is this coding that gives you so much control. It's going to be great. Now there's also this other thing called RStudio. What is RStudio? You'll also have to download it so you can do R stuff in RStudio. It's basically like a nice environment that you can keep everything nice and organized and tidy. It's technically called an integrated development environment, an IDE. Don't worry about that. And it's just much easier to use R inside of RStudio. This is what RStudio looks like, and I will go into more depth in future videos. But basically here is where you could write like in a notebook and write all your code here. Then you would actually run your code and it would spit out an answer here. So this is basically where you would see the answer. This is called your global environment, and this is where objects like different data sets that you load in are stored. And this has a few different functions like help menus and plot windows, and we'll look at all those later. So finding help in R, sometimes also known as debugging. Sometimes, many times, things don't work as they should, and sometimes R will throw back an error that seems kind of cryptic and confusing. But an invaluable skill in coding and much of life is being able to Google proficiently. So if you ever get an error, I recommend copy-pasting that error directly into Google. And most likely, because we're doing intro level R, most likely whatever problem you're hitting, somebody else has already encountered it and they asked it on these public forums, and very kind people out there respond and show some of the ways to get around the problem or how to answer it. One of the first things you'll probably see if you were to type an error into Google is a website called Stack Overflow. I use this all the time, probably at least once every time that I'm coding for my own research, my own work. Also, working together helps. You'll be doing some pair coding when you're working on your projects together. I'll show you how to do that in Zoom, and it's basically just both of you looking at the same screen together and typing and working away. And you might be getting an error, and one of you who's doing the coding might be like, I don't know what's wrong. And your friend will say, you're missing a period, yo. Just put in that period, and then bam, everything is fine. So having another set of eyes can be really helpful. And lastly, of course, because I'm the one making you do this, I will be here to help you every step of the way. Please reach out to me. I'm happy to try to help. But as a little aside, whenever you do reach out for some sort of coding help, you can't just say, this isn't working. I don't know why it's not working either, unless you give me more context. So first try to find the answer on your own a bit, or work with a partner. And when you can't find the correct answer, something's not running, reach out to me. Show me what the error is. Show me what you've tried. Show me what website maybe you've looked at. And then we can get to that answer more quickly together. Now, as a quick side note, you might be wondering, where does this word debugging come from? I think it's time for our very first historical moment. Our very first historical moment is brought to you by Grace Hopper. Grace Brewster Murray Hopper was an American computer scientist and United States Naval Commodore. She was turned away from enlisting multiple times in the Navy for various reasons, such as being too old, she was 34 at the time, too small, she was about 15 pounds under the weight minimum, and because her math skills were needed elsewhere. She enlisted in the Naval Reserves eventually. Now here's the fun fact about that debugging. We debug code when it doesn't run or when it has errors. The reason it's called debugging is because an actual insect, a moth, found its way in Mark II, a computer at Harvard Hopper was working on, and caused some trouble. Legend has it was Hopper that stated that they were debugging the system. Now, there have been other accounts people using that term before she did, but hey, it's a good story. Let's keep up with the lore. Here is the actual bug. Now back to our regularly scheduled programming. So I'm sure at this point you're considering dropping, please don't. And you're probably saying, why are you making us do this? Some of you might be thinking that, oh, that's not for me, I don't do math, or I don't do coding. Says who? I mean, maybe you're telling yourself that, but it's not like there's this part of your brain that you are incapable of doing math or learning code, with few neurological exceptions. Even if you never use R again in your life, I want to give you the smallest little taste and experience of doing real data analysis. By the end of this, you will have typed out and run some code all by yourself. And that is something to be very proud of. You will be ahead of the game and have done something that not many people do and many people actively avoid. I personally wish I would have been introduced to R as an undergraduate. I would have been much further along. If you are thinking of graduate school, R can be an invaluable skill. And if ever, for some reason, for some other class or a job, you need to analyze some data, you'll be able to fall back on some of the skills that you learn here, like writing code, creating a visualization, and interpreting results. And remember, R is free. You will keep it forever, unlike many of the other softwares that some classes might make you use. You can do this. You really can. I thought for many years there's no way that I would ever do statistics, and here I am getting a PhD in it. I never thought that I could code, and here I am teaching you all to do some coding. I'm going to start picking up another coding language, Python, this semester. It is never too late to learn these things, and I am going to help you every step of the way. I want to empower you with these skills. So that's why I'm making you do it. Please don't hate me for it. Promise we're going to get through this. You got this. I believe in you. I am here for you. We're going to get through. Now that that's done, I'll see you in the next lesson.